Good morning to everyone. Okay, today we'll proceed to the new topic, which is a single phase system. Okay, you can see this topic in chapter 3 in your textbook. Okay, so for today we have 4 objectives. Okay, number 1 is on the liquid and solid density. Okay, I believe that. Okay, this one. Okay, I believe that you still remember that about the liquid and solid density. We already learned this topic in chapter 3. Okay, and then if we have a mixture for liquid, so how we going to determine the mixture density? So this is our second objective. And the third one is on the ideal gas. Okay, so actually for the chapter 5, we focus on the gas. Okay, that's why the topic name is on the single phase system, which is we focus on the gas. Okay, so under the ideal gas, okay, I will teach you, okay, on the ideal gas equation stage. Okay, I believe everybody known this equation, which is PV equal to nRT. And then another one under the ideal gas topic, we will learn about the standard temperature and pressure. Okay, or in the short form we call in the STP. And our last objective for today's lecture is on the ideal gas mixture. Okay, for ideal gas mixture, we have 2 laws, which is number 1 is a Dalton's law. Okay, this Dalton's law is based on the partial pressure. Okay, so the symbol of partial pressure is PA. Okay, small letter of P. Okay, and we have A, okay, subscript here. And the another one is on the Amagat's law. Okay, this one is based on partial volume. Okay, this 2 law is for the ideal gas mixture. Okay, now we start our lecture with the first objective, okay, which is liquid and solid density. Okay, this one is just for recall only. Okay, I believe that you still remember about the liquid and solid density. Okay, in chapter 3, okay, we learned that, okay, about the specific gravity for solid and liquid, which is, okay, the equation, okay, for the specific gravity for solid and liquid is equal to rho reference. This is a density. This is what? Density for substance. Okay, rho reference is density for water. This is at what? 4 degree C. Okay, so where we can get the value of specific gravity? Okay, why we need the specific gravity? Okay, I have lots of questions. So we use specific gravity in order to get the density of substance. So where we can get the specific gravity? Okay, so the value of specific gravity of several substances, okay, at a single temperature are listed in table 1 in appendix B, which is in your textbook. Okay, so you kena familiar okay, kat mana table 1 in appendix B. Okay, but the substance in your textbook tu very limited. So kalau you nak more extensive tabulation on the specific gravity, you can refer to Paris Chemical Engineers book. Okay, saya rasa yang ni boleh dapat online. Okay, this one is very important when you do your plan design too later. Okay, actually, okay, okay, like I told you before. Okay, so from the specific gravity, okay, from the specific gravity we can get the density. We can find the density of the substance for the solid and liquid. Okay, so density equal to M over V. Okay, so you remember this one? Okay, so actually we can convert from V, okay, from volume to mass by using density. Okay, and also if we want to convert mass to volume, we can use the density. Okay, I hope you still remember. Okay, jangan lupa walaupun kita dah pergi kepada topik yang baru, you jangan lupa topik-topik yang sebelum ni. Okay. Okay, so look here. Okay, I write here, changes in T or P do not cause significant change in liquid and solid. Okay, so for this one, if temperature dependence modest but sometimes important lah, not very important. Okay, biasanya for liquid and solid, okay, pressure dependence, okay, biasanya kita abaikan. Okay, biasanya kita abaikan. Okay, sebab okay, sebab apa nama, for liquid and solid, dia adalah incompressible substance. Okay, but for gas, it's a compressible substance. Okay, so dia adalah temperature, dia adalah untuk gas, dia adalah pressure dependence. Boleh? Okay, now, okay, kita proceed to mixture density. Okay, if for example we have a liquid A or liquid B, okay, so kita boleh kira the mixture density. Ada dua cara. We have two ways, okay, in order to determine the mixture density. Okay, first is we can assume volume additivity. Okay, what is the volume additivity? Okay, for example, you have 2 milliliter of liquid A mixed with 3 milliliter of liquid B. Okay, so how about the volume of the mixture? So we just write, okay, 2 ml plus 3 ml, we got 5 ml. Okay, this one is volume additivity. We assume volume additivity. Okay, so if we assume that volume additivity, we will use the equation 5.1-1. This one you can see, you can find it in your textbook. So how do you get this equation 5.1-1? Okay, so look at here, the derivation. Okay, so we know that for we need to assume volume additivity, which is V is a total volume equal to volume 1 plus volume 2. Okay, so volume, okay, volume equal to M over density. Okay, M is a total M, and this one, the symbol this one is a total density. Okay, which is we get M1 divided by rho 1 plus M2 divided rho 2. Okay, so we rearrange the equation. Okay, we bring M to right side. Okay, so we get this one, and from this one we get the equation here. Okay, so this equation, okay, is best for mixture of liquid species with similar molecular structure. So if we want to use this equation 5.1-1, okay, there are some rule, which is this equation is best for mixture of liquid species with similar molecular structure. For example, straight chain hydrocarbon such as pentane, hexane, and heptane. Okay, so another one, okay, in order to determine the mixture density, we use equation 5.1-2. Okay, for this one, I'm not sure how they get this equation, but we just use this equation. Okay, so from this one, okay, the another way to get the mixture of density by weight average of your component density. Okay, for this one, okay, dia tak ada rule. Okay, no general rule. Okay, so the difference between equation 5.1-1 and 5.2-2, which is for the equation 5.1-1, okay, dia digunakan biasanya untuk mixture of liquid species with similar molecular structure. Contoh dia macam yang saya bagi tahu tadi lah, pentane, hexane, and heptane. Okay, and then for the equation 5.1-2, so there's no general rule. Okay, so from here actually we can estimate the error in finding the accuracy of calculated value. Okay, where percentage of error equal to calculated minus theoretical divided by theoretical multiplied by 100. Okay, so now, okay, we try this example. Actually, this example is in your textbook. Okay, example 5.11. Okay, so the question is determine the density in gram per centimeter cubic of a 50 weight percent aqueous solution of sulfuric acid at 20 degrees C. Okay, both by first you have to looking up a tabulated value, and number 2 is assuming volume additivity of the solutions component. Okay, for number 1, okay, dia suruh tengok dekat tabulated value. Actually, this one you have to refer to the Paris Chemical Engineers book. Okay, so sebab tak ada, so saya letak dekat sini lah. Okay, dia punya table, okay, tabulated table untuk sulfuric acid. Okay, so daripada sini kita tengok, okay, kita tengok pada 20 degree C, and dia punya percentage is 50 weight percent. Okay, so daripada sini kita bawa, okay, di sini sini. Okay, and then we get the density, okay, of 50% aqueous solution of H2SO4 is 1.3951 gram per centimeter cubic. Okay, actually this one is the theoretical value where we get from the table. Okay, so now for the second one, we have to assuming volume additivity, which is we need to use the equation 5.1-1. Okay, so before we use this equation, we have to find the value of density for the pure component. Okay, so they have a 50 weight percent aqueous solution. It means that they have a 0.50%. They have a 0.5 weight percent of H2SO4 and 0.5. Okay, weight H2 weight of water. Okay, sorry. So 50 weight percent aqueous solution of H2SO4 mean that they have 50% of H2SO4 and another 50% is for water. Okay, so we need to find the density of water and density of H2SO4. Okay, so this one we get the value. Okay, this is also from the Paris Handbook. Okay, and then we get this value. Okay, so just you don't worry about the temperature. Okay, because this one is not much difference. Okay. So, and then we have to neglect the density change for H2SO4 between 18 degrees C and 20 degrees C. Okay, so we need to use the equation 5.1. Okay, so, okay, then we want to get the mixture density. Okay, so from here, okay, Xi, this is SI what? Is a mass fraction. So we get 0.5 divided by 0.998 for water plus 0.5 divided by 1.834. Okay, and then we get the density of mixture. Okay, sorry. Okay, and then we get the density of mixture, okay, which is 1.29 gram per centimeter cubic. Okay, so we can calculate the error. Okay, so error, how to calculate the error? How to calculate the error? So the value of calculated, which is this one, minus by value of theoretical, this is from the tabulated table, okay, in Paris Handbook, divided by theoretical and multiply by 100, we get around negative 7.3%. Okay, so how about, okay, so now please determine the density of 50 weight percent aqueous solution of H2SO4 at 20 degrees C using equation 5.12. Okay, so from equation 5.12, okay, 4.12 we get, okay, so we get the value of density of mixture is about 1.42 gram per centimeter cubic. And then when we calculate the error, we got 1.5%. Okay, so previous one we got what? We got 7.3%. 3% error. So it means that equation 5.1-2 is better than equation 5.1-1. Okay. So actually I prefer the equation 5.1-2. Okay, because for equation 5.12, okay, there's no rule for this equation compared to the equation 4.5.1-1. Okay, I hope that you remember this rule. Okay, rule for the equation 5.1-1. Okay, that's all for the liquid and solid and density of a mixture. Now, okay, we proceed to our third objective, which is on the ideal gases. Okay, so seperti yang saya bagi tahu tadi, okay, untuk topik kali ni single phase system ni, okay, kita fokus on the gas. Okay, on the gas. Okay, so first we will see the ideal gas equation of state. Okay, actually what is ideal gas, or sometimes we call as a perfect gas. Okay, ideal gas or perfect gas is an equation of states relates to molar quantity and volume of a gas to temperature and pressure. Okay, so the equation for ideal gas, okay, I believe everybody are very familiar with this equation, which is PV equal to nRT, or PV, okay, dia ada topi kat atas ni, okay, dot equal to N dot RT. Okay, this one apa ni? Kalau V ada dot, is a volumetric flow rate. And N dot dekat atas ni, okay, dia adalah apa? Molar flow rate. Okay, and then, okay, yang ni student selalu buat silap. Okay, this equation, okay, only used for gas, not for liquid and solid. Okay, if you want, it means that if you want to find the value of mole, okay, which is we want to use this value in order to solve the mass balance. Okay, so for gas we use this equation, okay, not for liquid and solid. Okay, for liquid and solid, okay, we can get we can get the mole or mass or volume, okay, by using specific gravity. Betul? Okay, please, okay, this equation is used only for gas. Okay, so why we use this equation for gas, not the specific gravity? Because, okay, look here, okay, look here, okay, sorry, look here, okay, there's no specific gravity for gas. That's why we have to use PV equal to nRT. Okay. Okay, what is P? P is a absolute temperature pressure of a gas. Okay, what is absolute pressure of, what is a absolute pressure? Okay, look here. Okay, you look here. Okay, P absolute equal to, okay, gauge pressure plus atmospheric pressure. Okay, remember, okay, absolute pressure equal to gauge pressure plus atmospheric pressure. Okay, so for the atmospheric pressure is equal to 1 atm or 1.01325 bar or 14.696, okay, psi or 760 millimeter Hg mercury, okay, or 101.325 kilo Pascal. Okay, actually you don't have to remember this value for atmospheric pressure. This one you can refer to the conversion table in your textbook. Okay, at front of your textbook. Okay. So sometimes, okay, ni biasanya trick. Okay, kalau dalam soalan tu, okay, biasanya kalau dibagi gauge pressure, okay, you tak boleh directly use, okay, the gauge pressure dan masukkan ke dalam equation PV equal to nRT. It means that you have to plus, you have to plus with the atmospheric pressure, and then we get the absolute pressure, and then you can use the absolute pressure. Okay, you can use this absolute pressure for the PV and RT equations. Okay, and sometimes, okay, in the question dia just cakap pressure. Contoh dia pressure untuk gas tu adalah 1 atm. Okay, so dekat situ dia tak bagi tahu pun dia adalah gauge ataupun atmospheric pressure. So we can assume that the given pressure is the absolute pressure. Okay. Okay, so V, okay, the capital letter of V and V dot, this one is represent as volume or volumetric flow rate. Okay, volumetric flow rate of the gas. N dot is number of mole or molar flow rate of the gas. Okay, R is a gas constant. Okay, so in your textbook, okay, it listed in the table on the inside back of the of your textbook. Okay, you boleh tengok nanti dekat belakang sekali tu ada list of gas constant. Okay, you boleh tengok, and then please be careful with the unit of R. Okay, because kalau you tengok nanti dekat belakang on your textbook, okay, the unit, they have a several unit for R. Okay. Okay, T, okay, is a absolute temperature of the gas. Okay, for absolute temperature, okay, you need to use a Kelvin, okay, and Rankine. Okay, unit Kelvin is a degree units Celsius. Okay, if for example, in the question they give you berapa? Bagi T equal to 23 degrees C. Okay, then you have to convert into Kelvin. Lepas tu baru masukkan dalam equation ideal gas equation. And another one is a Rankine. Rankine is a degree units for the Fahrenheit. Okay, so equation for ideal gas, okay, is applicable at low pressure, which is less than 1 atm, and high temperature, which is more than 0 degree Celsius. Okay, remember, okay, ideal gas is applicable for low pressure and high temperature. Okay, so the equation for, oh sorry, The equation for PV and RT, okay, we can also write like this. PV, this one right, cap equal to RT. Okay, V cap ni equal to V over N, okay, volume over mole or volumetric flow rate, okay, over mole flow rate, which is this one is known as the specific molar volume of gas. Okay. Okay. Equation for the ideal gas of perfect gas, okay, does not require a knowledge. Kita tak perlu ada knowledge pun about the gas species, because 1 mole of ideal gas, okay, at 0 degrees C and 1 atmosphere occupies 22.415 liter. Okay, whether the gas is argon, nitrogen of any other single species or mixture of gases. Okay, so you tak perlu tahu pun what is the gas species. Okay, kalau kita nak guna equation for ideal gas or perfect gas. Okay, you tak perlu tahu mengenai gas tu spesies apa. Okay. So, the ideal gas equation of states, okay, is an approximation and it works well under some condition, okay, at temperature above, as I told before, at temperature above about 0 degrees C and pressure below 1 atm, okay, but at other condition may lead a substantial errors. Okay, you tengok rule of thumb to verify the ideal. So kita boleh verify, okay, the ideal gas law is a good approximations, okay, by using the rule of thumb, which is, okay, kita boleh tengok arrow dia, okay. Kita boleh tengok error untuk error dia. If error dia less than 1%, it mean that dia accurate lah. Okay, so kita boleh tengok kat sini, kita boleh kira, okay, V ideal equal to V over N equal to RT per P much dia lagi besar daripada 5 liter per mole. This one is for diatomic atom. Okay, contoh-contoh diatomic atom example is nitrogen gas and oxygen gas. This one is diatomic gas. Okay, kalau you nak guna kalau you nak calculate error, okay, daripada yang ideal gas equation tu, for diatomic gas you guna these equations, and another one for the other gas we can use this equation. Okay, so kalau dia untuk diatomic, kalau lebih daripada 5 liter per mole, it mean that it's accurate lah, okay, by using the PV equal to nRT. Okay, kalau untuk other gas, if more than 20 liter per mole, it mean that it's accurate. Okay, so you use this, okay, you use this one, okay, in order to see the accuracy of your answer. Okay, look at this example. Okay, so propane at 120 degrees C and 1 bar absolute pass through a flow meter that reads 250 liter per minute. What is the mass flow rate of the gas? Okay, kita nak dapatkan mass flow rate. Okay, so macam mana kita nak dapatkan mass flow rate? Okay, this is a gas, okay. So, kita guna PV equal to the nRT, and then we find the value of molar flow rate, okay. So, we get here, okay, from the molar flow rate, okay, for the molar flow rate, we can get mass flow rate, okay, by multiply molar flow rate with the molecular weight, and then we can get the value of mass flow rate, which is this value. Okay, nanti you try lah buat. Okay, cuba buat dapat tak this value 337 gram per minute. Okay, so look at the second calculation. Okay, 100 gram of N2 is stored in a container at 20 degree Celsius and 3 apa nama? PSIG. What is the meaning of PSIG? This one is pound per square inch gauge. Okay. So, okay, what is the difference between calculation 1 and calculation 2? Okay, here, okay, like I said before, this one, okay, the pressure given is a gauge. Okay, in a calculation 2, the pressure given is a gauge pressure. Okay, but in here, okay, this one is absolute pressure. Okay, this one for the calculation 1, we can directly, okay, masukkan dalam equation PV equal to nRT. But this one cannot. Okay, so it means that we have to find the value of absolute pressure, which is gauge pressure plus P atmospheric. Okay, so okay, look at question number 1. Assuming ideal gas behavior, calculate the container volume in liter. Okay, and the question number 2, disuruh apa? Verify that the ideal gas equation of state in is a good approximation for the given condition. Kita nak tengok, kita kena verify kan, is it the ideal gas equation of state is a good approximation for the given condition. Okay, macam mana kita nak tengok yang tu? Seperti yang saya tunjuk tadi lah. Okay, kita boleh kira dia punya V ideal dia kan, kita boleh tengok kan. So kalau tengokkan yang calculation dalam calculation tu N2 ni untuk diatomic gas, betul tak? Diatomic gas. Okay, so we try to do question number 1 first. Okay, for calculation 2. Okay, so assuming ideal gas behavior, calculate the container volume in liter. Okay, so kita guna apa? PV equal to nRT. Betul tak? And then before we do this, before we solve these equations, okay, so this one, okay, the given is in mass of nitrogen gas, and then we have to convert this one into mole first. Okay, and then we have to find the value of P absolute and this temperature also. Okay, we have to change to the absolute temperature. Okay, which is in Kelvin. Okay, T equal to 23 degree C plus 273 Kelvin. Betul tak? Okay, look at this solution. Okay, as I told you before, we have to find, okay, the value of mole. Okay, and then we get 375 mole, and T we have to convert Celsius to Kelvin for the absolute pressure, and then we get the 23 plus 273 equal to 296 Kelvin. Okay, and then we can we find the value for the absolute pressure where equal to 3. This is a gauge pressure plus 14.7. Okay, this one is the PSIG, right? This one is the PSIA. Okay, which is apa? Pound square inch absolute. Okay, so kita rearrange, kita akan dapat V lah. Okay, V equal to nRT. Okay, remember that you have to careful choose the value of R. Okay, that's why every time you write the equation, you want to solve the equation, please write your units. Okay, then you boleh cancel out and then you get the value of you get the volume for a nitrogen gas is around 72 liter. Okay, 72 liter. Okay, now so number 2. Okay, number 2, to verify the assumption of ideal gas behavior for N2. Okay, this one N2 is a diatomic gas. Okay, we know the value of volume and we know the value of mole. So then, okay, we divided volume over mole, we got 20.2 liter per mole, which is more than, which is greater than 5 liter per mole. Okay, so the ideal gas equation of state, okay, yield an error of less than 1%. Kita boleh cakap bahawa bila kita guna ideal gas equation of state, okay, dia punya error less than 1%. It means that it's accurate lah to use PV equal to nRT for this problem of, okay, for this problem. Okay, so now we proceed to still under the ideal gas. Okay, we will see about the standard temperature and pressure. Standard temperature and pressure, which is STP. Okay, okay, so when we use the okay, so when we use the equation PV equal to nRT, okay, so we need to use the gas constant, okay, but you can avoid to use the this gas constant, okay, by using these equations. Okay, by using this equation, you do not need a value for R. Okay, which one is PV, okay, divided by PS multiplied by VS. VS is standard pressure, standard volume, standard mole, and standard temperature. Or, okay, we can write the equation like this. Okay, PV equal to PS, okay, multiply by V cap S. Okay, V cap S ni adalah apa? Apa yang saya cakap tu? Cuba ingat. VS adalah molar specific molar volume. Okay, specific molar volume. This is a specific molar volume. Okay, which is VS equal to VS divided by NS. Okay, so you can see in your textbook table 5.2-1. Okay, for inside the table 5.2-1, we can see the standard condition for gas. Okay, they have a system, they have unit for SI, CGS. Okay, CGS is centimeter gram second, and the American Engineering Unit. Okay, so kita tengok, okay, at dekat standard temperature pressure 273 Kelvin. Okay, pressure, standard pressure 1 atm. Ni 273 Kelvin ni sama juga dengan 0 degree C. Okey, pada satu atmosfer 273 Kelvin, dia punya volume adalah 0.022415 meter kubik, okey, dekat 1 mol. Okey, standard mol adalah 1 mol. Okey, so you boleh guna this equation. Kalau you tak nak confuse, guna R. R ni you kena hati-hati seperti yang saya kata tadi. You kena hati-hati pilih sebab value of R ni ada banyak, okay, and ada different unit. Nanti you boleh tengok dekat belakang buku you ya, okay. So that you can use this one, okay, by using this equation, okay. Okay. So biasanya kalau dalam soalan, okay, you tengok ada term standard cubic meter. Okay, kadang-kadang dia bagi dalam unit standard cubic meters or SCM. Okay, dia adalah denote M3 STP, and standard cubic feet or SCF denotes as a feet cubic STP. Okay, so you tengok kat sini values of the standard specific volume, molar volume. Okay, macam mana kita nak cari values of the standard specific molar volume, which is apa? Vs. Okay, daripada previous table ni, okay, kita boleh tahu kan, daripada previous table Vs ni adalah equal to, okay, yang ni kan, Vs over Ns. So you divided this one, you divided by this one, okay, and then you will get this value, okay, 22.4 meter cubic per kilomole. Okay, kalau you nak buat dalam mol pun boleh, okay, or 22.4 liter per mole, okay, or 359 feet cubic STP per mole. Okay, cuba you tengok contoh sini. Okay, let's say you have 450 meter cubic STP per hour of gas flow rate inlets into the combustion reactor, and then you have to calculate and then you need to calculate the question is you need to calculate the gas molar flow rate of gas inlet in mole per hour. Okay, so this one is what? This one is Vs. Betul tak? Okay, so we know that the specific molar the standard, kita tahu the specific, the value of standard specific molar volume, Vs equal to Vs. Okay, kita boleh tak ni lah untuk menunjukkan dia flow rate divided by apa? Ns. Betul tak? This one is flow rate. Okay. Okay, so diberi adalah Vs. And this one, this value we know, right? Okay. So we take 22.4 meter cubic per kilo mole. Okay, and we know the value of 450 meter STP per hour, okay, and divided by Ns, and then we can get the value of Okay, this one is not NS. Okay, sorry. Because the standard is 1 mole, right? So this one got N. Okay, so N equal to 450 meter Cp, okay, per hour, okay, divided by 22.4, okay, meter 3 kilomol, okay, dia nak dalam mol, okay, so you kena convert kilomol kepada mol, which is 1 kilomol, oops, sorry, tak muat pula, okay, 1 kilomol per 1000 mol sama juga dengan 1 kilomol, am I right? Okay, so nanti you akan dapat jawapan dia. Okay, jawapan dia nanti bila you kira akan dapat lebih kurang 20,089.27 mol per hour. Okay, so now look at this example. Okay, for this is also example in your textbook. In example 5.2-2. Okay, so read this. You read these questions. Okay, blah 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 blah. Butane at 360 degrees C at 3 atm. Okay, absolute flows into a reactor at a rate of 1,100 kilogram per hour. Then you have to calculate the volumetric flow rate. Okay, disuruh cari apa? Volumetric flow rate of this stream using conversion from standard condition. Okay, kalau disuruh guna using conversion from standard condition, okay, so it means that you have to use this equation. Betul tak? You have to use these equations. Okay, is these equations. Okay, Vs this one equal to, okay, Vs equal to Vs pada and S. Okay, so okay, daripada situ, okay, then you have to first what you should do, okay, T, okay, because it's given in the degree Celsius, you have to convert to Kelvin first for the absolute temperature, and given is M, molar flow rate, mass flow rate, and we have to convert mass flow rate to molar flow rate. Okay, after we convert, we get 19, okay, kilomole per hour. We get 19 kilomole per hour. And from here, okay, so we put inside this equation, okay, this one we rearrange because we want to find the value, the volumetric flow rate. So we arrange and then it's become like this. Okay, so then, okay, and then okay, kita masukkan dalam kita masukkan nilai value yang kita ada, and then we get the volumetric flow rate. Okay, so we get 329 meter cubic per hour. This one you can try. Okay, you can try, and also you can try by using the PV equal to nRT. Okay, you can use this equation. Okay, please try guna this equation, and then okay, sepatutnya you kena dapat jawapan yang sama lah. Okay, 329 meter cubic per hour. Boleh? Okay, so look at this example 5.23. Okay, sometimes we have two condition. Okay, initial and final condition. Okay, which is we can write. Okay, so look at here. Okay, they say that 10 cubic feet of air at 70 degree Fahrenheit at 1 atmosphere is heated to 610 degree Fahrenheit and compressed to 2.5 atm. What value does the gas occupy in its final state? Kita nak tahu volume yang occupy in the final state. Okay, so kita ada initial and final condition, and then before that, okay, this pressure, okay, this pressure dia tak cakap pun kan, adakah gauge ke, adakah this is atmospheric pressure ke, okay, for also for 2.5 atm. So this one we can assume that the pressure is already in the absolute pressure. Okay, so then okay, kita buat, okay, kita lukis gambar PFD sikit lah. Okay, N1 of air, okay, this is mole initial, okay, mole final. Okay, so tulis dekat sini P, okay, P initial condition 1 atmosphere, T 70 degree C, okay, V, okay, 1 sama juga dengan, okay, V initial dibagikan 10 feet cubic. Okay, so we want to find the value of final volume. Okay, final volume. Okay, so dekat sini, okay, dia tak ada menyebabkan reaction pun kan. N1 equal to N2. Okay, so kita buat dulu dekat initial state ni. Kita buat dekat initial state ni. Okay, kita buat P1. Okay, V1 sama juga dengan N1 RT1. Betul tak? And for the final state, P2, okay, V2 equal to N2 RT2. Okay, so we rearrange, okay, this equation. N1 equal to P1 V1 RT1 and N2 P2 V2 RT2. Okay, and then we know this relationship, which is N1 equal to N2. Betul tak? So we substitute equation 2 and 3 into equation 1. Okay, we substitute equation 2 and 3 into equation 1. We get this relationship. Okay, so when we get this one, okay, we know the value of P1, V1, T1, P2, T2. Okay, so we can rearrange this equation. Okay, become like this, and then we get the final volume, which is 8.08, okay, feet cubic. This one you can try. Okay, so but please be careful. Okay, this T, okay, this T is in the degree Fahrenheit. Okay, so you have to convert into absolute temperature. Okay, so if Fahrenheit, you have to convert into Rankine. You cannot directly put 70, for example, this one is V1, 70 degree C. Cannot. Okay, so you have to convert this one to Rankine. Okay, so this is, okay, you see this table? This table, okay, how you going to convert, okay, for Celsius to Kelvin or Fahrenheit to Rankine. Okay, boleh? Okay, now, okay, kita habis untuk ideal gas, okay, the PV equal to nRT, okay, kita guna untuk pure gas substance. Okay, we use for the pure gas substance. Okay, so how about we going to find value of apa a mole ke, okay, mole fraction ke, okay, for the mixture. So now we proceed to our last objective, which is ideal gas mixture. Okay, so we start with the Dalton's law. Okay, so for Dalton's law, okay, Dalton's law use a partial pressure. Okay, so what is a partial pressure? Okay, partial pressure, okay, is the pressure that would be exerted by moles of A alone in the same total volume V at the same temperature. Okay, remember, this is, okay, remember, we have, okay, the equation for ideal gas. Okay, ideal gas, which is PV equal to nRT. This is equation for the individual gas ataupun pure gas. Okay, so and then we can write a partial pressure equation. Okay, which is PA. Okay, so for PA is a partial pressure. This one pressure here is partial pressure. P is in the small letter. Okay, multiply by V volume equal to NA. Okay, mole for gas A multiply by RT. Okay, so this is equation 2 and the previous one is equation 1. Okay, so then we dividing the second equation by the first yield. Okay, so we divided the second equation P A V equal to P V, okay, N A R T over N R T. Okay, this one cancel out. Okay, so we get this equation, which is PA over P equal to NA over N equal to Y. Okay, NA per N. Okay, NA per N. What is this? This is a mole fraction of A. Remember? Okay, previous one. If you want to get the mole fraction of A, it means that mole of A divided by total mole. Okay, so it means that P, this one, okay, the apa nama? Capital letter of P and capital letter of B and capital letter of T. This one is a total pressure, total volume and total temperature. Boleh? And is a total mole. Okay. So, and then we rearrange, okay. Okay. So, PA equal to PA per P ni, okay, kita boleh rearrange dengan mole fraction ni, kita akan PA sama juga dengan YA per YA multiply by P. So for gas, okay, we can get the mole fraction by using an extra cara, which is we can get from the partial pressure divided by P. Okay, beside using the mole A, okay, per total mole, we can use, okay, partial pressure per total pressure untuk dapatkan mole fraction of A. For example, okay, so this one is applicable for gas only. Okay, for gas only. For liquid and solid boleh guna tak PA over P untuk cari mole fraction? Okay, so tak boleh. Tak boleh. Okay, so then kita tahu bila kita tambah partial pressure, for example, partial pressure A plus partial pressure B, kita akan dapat plus bla 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 bla, kita akan dapat total pressure. Okay, so we know that PA equal to YA P tambah YB P tambah sama juga dengan P, betul tak? Tapi YA ni, P ni kita tulis macam YA tambah YB tambah dot P sama juga dengan P. So then we get this equation. Okay, and then you have to remember YA tambah YB tambah bla 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 equal to 1. Okay, and also this one same. Okay, and then we bring this P here. So we get YA tambah YB tambah sama juga dengan 1. Okay, so this one is known as a Dalton law. Okay, Dalton law based on the partial pressure. Sekarang ni tak nampak lagi macam mana nak gunakan untuk mass balance kan, tapi boleh nampak sikit lah gambaran bahawa kalau kita guna Dalton's law, kita mesti boleh cari mole fraction. Mole fraction. So now we proceed to the Amagat's law. So Amagat's law ni dia based on the partial volume. So what is the partial volume? The volume that will be occupied by mole A, of A alone at the total pressure P at the same temperature T of the mixture. So again, ideal gas equation, we got PV equal to nRT, and partial pressure equation. Oh, sorry, this is not partial pressure equation. This is for volume. Oh, partial volume, sorry. Partial volume equation. Which is P, multiplied by VA partial volume equal to NART. What is the difference between the Amagat's law? Kalau Amagat's law dengan Dalton law. Kalau Dalton's law here, Dalton's law dia buat partial, dia based on partial pressure kan. Partial pressure RT. Partial pressure, and this one kita guna total pressure. So this one we use partial volume, and this one is partial pressure. Equal to NART, equation 2. So again we dividing in the second equation by the first one. Dividing PVA equal to PV equal to NART over nRT. So we get VA per V equal to N. This one N. NA per N equal to YA. This is a mole fraction of A in the gas. So you see, for Dalton's law, we have another equation to calculate the mole fraction by using the partial pressure divided by total pressure. But for the Amagat's law, we use the volume, partial volume divided by total volume, and then we get the mole fraction. Okay. So here I write a note here. The volume fraction of a substance in an ideal gas, in an ideal as mixture equal to the mole fraction of the substance, which is what? The volume fraction, okay, of the substance, okay, for the is an ideal as mixture equal for the macam pelik ayat ni kan. Okay, the volume fraction of a substance in an ideal gas mixture equal to the mole fraction of the substance. It means that volume fraction sama juga dengan mole fraction. Okay, contoh kalau nanti dia bagi persen, okay, 50 volume percent, it means that it's equal to 0.50 mole percent, okay, for the Avogadro's law. Okay, and then VA plus VB plus blah 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 blah, and then you get total volume. Okay, this one we call as the Avogadro's law. Okay. So look at this example. Okay, this example, okay, how we going to use the Dalton's or Avogadro's law, okay, to solve your mass balance, okay. And as I said previously, okay, so from the Avogadro's law or from the Dalton law, we can get the mole fractions, okay. So you please see the example in your textbook, example 5.2 dash 5. 5.2 dash 5. Okay, you read. Okay, so the questions are: what is the molar composition of the stream leaving the compressor? And then what is the volumetric flow rate of nitrogen entering the evaporator if T equal to 27 degrees C and gauge pressure is 475 millimeter Hg. Okay, look at this example. Actually, this example words is quite confusing. Okay, kalau you tengok dekat sini, liquid acetone, okay, is fed at a rate of 400 liters per minute into a heater chamber where it evaporates into a nitrogen stream. Okay, so this one, okay, this statement is mean that, okay, liquid acetone ni, okay, dia akan combinekan dengan liquid acetone punya stream, okay, akan combine dengan nitrogen stream dan akan masuk dekat evaporator. Okay, so lepas tu the gas leaving the heater is dilute by another nitrogen stream flowing, okay, at a measured rate of 419 meter cubic STP per minute. Okay, and then the combined gases are then compressed. Okay, dia compress, dia masuk dekat compressor. Okay, sebenarnya saya tak suka sangat, okay, dengan gambar yang dilukis kat dalam buku you, tapi tak apalah. Okay, saya tunjuk dia dulu, nanti saya tunjuk saya punya calculation. Okay. So then, dia cakap combined gas compressed to a total pressure, okay, tapi diberi adalah gauge, okay, gauge pressure which is 6.3 atm at a temperature 325 degrees C. Okay, the partial pressure of the acetone, okay, dia bagi partial pressure PA, ataupun you boleh tulis PAC lah nanti ya. Boleh tulis P-acetone, 501 millimeter H mercury. Okay, atmospheric pressure is 763 millimeter mercury. Okay, so nanti you akan lukis gambar, you akan dapat macam ni lah. Okay, first you kena lukis gambar you punya PFD. Okay, biasanya lepas keluar daripada evaporator kita ada dua stream kan? Kan? Ada dua stream, betul tak? Cuba tengok balik yang dalam slide. Okay, slide proses unit proses punya slide yang saya pernah bagi dulu. Okay, sepatutnya bila keluar daripada evaporator ada dua stream, tapi kat sini satu stream je. So kita boleh katakan semua ni telah gas yang keluar tu semua dalam bentuk vapor, tak ada pun yang jadi liquid. So that's why they have only one stream, okay, after keluar daripada evaporator. Okay, so from here, okay, we can calculate the degree of analysis. Okay, degree of analysis for the overall. Okay, for overall kita ambil dekat mana? Ambil kat sini kan? Okay, kita ambil kat sini. So we have 3 unknowns, N1, N4 and Y4, and we have 2 mass balance equation, which is nitrogen gas and acetone, and okay, we have one process pack. Okay, because given is partial pressure of acetone. Okay, so we can use this one. Okay, we use this relationship, which is partial pressure equal to Y equal to mole fraction multiplied by total pressure. Okay, so this is a step. Okay, as always, molar quantity and absolute T must be used. It means that, okay, if given in the mass, okay, you have to you have to convert into molar quantity, and please, okay, you have to use the absolute T and absolute P. Okay, and then this one, okay, convert mass or volume to mole and degree C to Kelvin, and use table B 5 to 1 for data calculation. Okay, this one is for the data for the standard temperature pressure. Okay, so this is my solution. Okay, for my solution, okay, I go step by step actually. Okay, first we have to draw the PFD. Okay, you tengok kat sini line sikit sebab saya just put mixer here. Okay, sebab dia kata tadi, okay, sekejap saya check dia punya soalan. Okay, dia kata the gas leaving the heater, okay, is dilute by another nitrogen stream flowing blah 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 tu. Okay, so dekat mixture ni dia combine, and then lepas combine, okay, yang gas yang keluar daripada mixer ni dia akan compress. Lepas tu dia akan hasilkanlah, dia akan keluar compress gas tersebut. Okay, so lepas tu second step saya, okay, ni sebenarnya boleh ikut step by step how to solve the mass balance kan. So first, okay, second, okay, so kita boleh kira dia punya basis. Okay, kat sini kalau you tengok dekat dalam this example, they have 2 bases, which is you can use 400 liter per minute liquid acetone at inlet stream, or you can use 419 meter cubic STP per minute nitrogen feed to the mixer. Okay, fed to the mixer. Okay, so lepas tu baru saya kira overall degree of freedom. Okay, overall. So you ambil overall ni lah. Macam yang saya lukis ni. Okay, so seperti tadi jugalah. Even dia lukis macam tu, saya lukis macam ni. Saya still dapat dia punya overall degree of freedom adalah equal to 0. So we can solve the mass balance by using the overall boundary. Okay, so first unit conversion. Okay, you have to do unit conversion first. Okay, so for unit conversion, okay, because this one dia beri dalam volume metric flow rate. So daripada volume metric flow rate, so you boleh convert to mass flow rate dulu kan, guna density. Okay, so nanti you boleh dapatkan SG acetone. Okay, this one SG acetone you akan dapat 0.791. This is from table B1, and also molecular weight of acetone, because daripada M kita nak jadikan N guna molecular weight, betul tak? Okay, so actually benda ni you kena ingat lah ya. Kita boleh convert B to M, okay, guna density, M to N guna molecular weight. Okay, so then daripada situ, okay, kita boleh convert okay, daripada V ni kepada N, tapi kita kena convert dulu V ni kepada mass flow rate. Lepas tu daripada mass flow rate kita convert kepada molar flow rate, and then from here we get this value. Okay, for 5447.66 mol acetone. Boleh? And then dia bagi apa? Dia bagi apa? Okay, volume metric flow rate, okay, dekat STP. Okay, so kat sini pun you boleh tukar kepada mol. Okay, so you boleh divided by, okay, apa, standard apa ni, molar volume. Okay, standard molar volume. Betul tak? Standard molar volume. Betul tak? Standard molar volume. Okay, check ya. Sekejap saya check. Saya pun lupa juga. Standard specific molar volume. Okay, this one is standard specific molar volume. Okay, standard, sorry, molar volume. Okay, so you bagi kat situ, you akan dapat molar flow rate. Okay, daripada partial pressure, dia bagi partial pressure kan, daripada partial pressure you boleh cari, okay, daripada sini, okay, you boleh cari mol fraction, okay, untuk acetone. Okay, you boleh cari mol fraction untuk acetone. Tapi before that, diberi adalah, okay, untuk P ni, okay, diberi adalah gauge pressure. So, apa yang you perlu buat, you kena cari absolute pressure. So, bila you cari absolute pressure, you akan dapat 5551 mm mercury. Okay, so you boleh buat macam ni. Okay, so tadi dekat yang stream yang keluar daripada kompresor, okay, mol acetone adalah Y minus Y3. So kita nak cari Y, nak 1 minus Y3 equal to Y, okay, acetone bahagi juga dengan P, partial pressure of acetone, divided by total pressure. So you akan dapat 0.0903 mol acetone per mol. Okay, bila dah dapat mole fraction for acetone, and then we can get the mole fraction for nitrogen gas. Okay, so the question number 2. Apa question number 2? Dia suruh cari apa? Part 2, dia suruh cari apa? What is the volumetric flow rate of the nitrogen entering the evaporator? Okay, if the temperature and pressure of the stream at 27 degrees C and 475 millimeter mercury gauge. Okay, so dia suruh cari apa? Volumetric flow rate for nitrogen yang masuk ke dalam evaporator. Okay, yang ni you boleh guna PV equal to nRT. Okay, so you boleh guna PV nRT sebab yang kat sini dia suruh cari nitrogen je kan, which is for the pure gas. So kita boleh guna PV equal to nRT. So nanti kita rearrange this one, we got this value of V. Okay, so V equal to this equation, and then we get the value of volumetric flow rate is around 546.85 meter cubic per minute. Okay, kalau you macam takut nak guna, kalau kat sini, kalau saya guna PV and RT, saya kena tahu value R kan, gas constant. Kalau you tak nak guna this one, okay, you boleh guna standard temperature pressure. Okay, which is mana? Okay, you boleh buat macam PV, okay, PSBS, okay, equal to apa? NT NS TS. Boleh? Okay, you boleh guna juga this equation. Kalau you tengok dekat buku you, dia guna this one. Okay, dia guna this one. Ni tak ada ni tak ada. Okay, dia akan guna this one. Bukan tak ada. Okay, so this one can get from table 5.21. Okay, kalau buku you dia guna standard temperature pressure untuk dapatkan V ni. Okay, tapi untuk saya guna PV equal to nRT. Okay, it's up to you. Okay, so that's all for today lecture. Okay, so kat sini saya boleh concludekan bahawa okay, untuk gas, okay, untuk ideal gas, okay, untuk pure substance, kita boleh guna PV equal to nRT untuk dapatkan bilangan mol. Okay, daripada bilangan mol kita boleh convert kepada mass. It's up to you lah. Okay, kita perlukan bilangan mol kadang-kadang untuk solvekan kita punya mass balance. Kenapa kita guna PV nRT? Okay, sebab okay, untuk gas kita tak ada specific gravity. Okay, untuk liquid kita boleh guna specific gravity kan. Okay, daripada specific gravity kita boleh dapat density. Daripada density kita boleh convert daripada volume kepada mass and mass kepada volume. Okay, daripada mass pula kita boleh guna molecular weight untuk convert kepada mole, which is that value okay is needed for the mass balance. Betul tak? So, kita ada reason kenapa kita belajar single phase. Okay? Kenapa tiba-tiba kita kena belajar about the single phase. But remember that, okay, PV and RT only for gas. Okay? Not for liquid and solid. And another one, if we have a mixture, so ideal gas mixture, we have two law. Okay, which is Dalton's law, which Dalton's law, we use a partial pressure, and another one is Amagat's law, okay, which is we use the volume, partial volume. Okay, beside, okay, so from the Dalton's and for the Amagat's law, we can get the mole fraction of a substance A, for example. Okay, so previously, if you want to get the mole fraction, we divided into, okay, mole of substance A per total mole. But if you use the Dalton's law, we can use another equation, which is partial pressure divided by P. Okay, this one is only for gas. Nanti jangan nak memandai-mandai, bila liquid pun you guna equation partial pressure bagi dengan P untuk dapatkan mole fraction. Nanti jawapan you salah. Okay. So, untuk Amagat's law, okay, dia kata apa? Volume fraction sama juga dengan mole fraction. Okay. So, volume fraction sama juga dengan mole fraction. Okay. So, itu saja. So, you boleh try semua yang example yang saya tunjuk kat dalam slide ni. Okay, cuba buat sendiri. Kalau setakat dengar saya cakap, saya rasa you tak faham. Okay. Apa-apa you kena buat balik. Boleh? You kena buat balik and then try to understand. Okay, if you don't understand, you can ask me through WhatsApp. Okay, so nanti I also will provide you the exercises. Okay, maybe tomorrow I will upload the exercises in the evening. Okay, thank you very much.